Hey guys, so today we're going to be talking about Chapter 4 for your Math 200 class. Chapter 4 is all about describing the relation between two variables. So we're going to start with section 4.1, which talks about scatter diagrams and correlation. So first thing we're going to do is go through a couple of definitions. Now, the first is the difference between the response and then the explanatory slash predictor variable. Explanatory or predictor variable are one and the same, just two terms for the exact same thing. But the response variable is the variable whose value can be explained by the value of the explanatory or predictor variable. So basically what we do is we use this predictor variable to help us predict the value of the response. Now, a scatter diagram is just a visual representation of this. It's just a graph. It shows the relationship between two quantitative variables that are measured on the same individual. Now, each individual in the data set is going to represent or be represented by exactly one point in the scatter diagram. Now, the explanatory variable is plotted on the horizontal axis, and then the response variable is going to be on our vertical or our y-axis. So the data that you see at the right are based on a study for drilling rock. So what some researchers wanted to do was determine whether the time that it takes to dry drill a distance of 5 feet in rock increases along with the depth at which the drilling begins. So the depth at which the drilling actually begins is going to be your explanatory or your x variable, and then the time in minutes to drill 5 additional feet is going to be the response variable, which is your y. And so the first thing we want to do is draw a scatter diagram of the data. So if we take a look at these data points right here, you'll see that if we start at 35 feet, it takes us 5.88 minutes in order to drill 5 additional feet. But if we kind of work our way down, you'll notice that there's sort of a trend where it looks like it's seeming to kind of take longer. So what we're going to do is we're going to describe this relationship, but first we want to look at a scatter diagram of the data. So if you look here, we have the depth at which drilling begins, that's our x variable, right along our x-axis, and this is in feet. And then we have our time to drill 5 feet in minutes right here along our y-axis. And each one of these little dots represents one of our data items from the previous page. So for example, if we go back for just a minute, at 35 feet, it takes 5.88 minutes, so that's going to be this first data item right here. And then at 50 feet, it takes 5.99 minutes, so that's our next data item. Now, this is a very easy graph to get in StatCrunch, so let me show you guys how to do that real quick. So if I pop over to StatCrunch, all I have to do is go to Graph, and then, let's see, it's a scatter plot. And I'm going to select my x variable right here, which is going to be my depth, and then my y variable. And I could add a title here. I could call this, let's see what we called it here, depth versus drilling time. So if we do compute, it just creates this nice little scatter diagram here, which is exactly the same thing that we just had. Now the nice thing about when you bring it up in StatCrunch is you can mouse over any of these little data points and it shows you exactly which data this particular point is coming from. So for example, if we look at this point right here, that was, let's see, depth at which drilling begins, it was 75 feet, and it took 6.74 minutes in order to drill 5 additional feet, starting at 75 feet. So if we come back over here, let's look at a couple of different types of relations that we might have based on their scatter diagrams. So what we can see here is that for this first one, for A, we have kind of this nice linear sort of relationship, okay? So we have our explanatory variable versus our response, and you can see that when all of the data items are plotted together, it sort of creates this linear shape. Now, this one is also linear. This has a different type of relationship, but it still is linear. But if we look down here, what you'll see is we see some kind of funny shapes. This sort of looks like a parabola over here. This looks like a cubic function. So these two, it's not that there is no relation, it's that there's some relation that's not linear. So all we would say for that type of pattern that we might see would be that these two are nonlinear relations. But if we look at this over here, these kind of just appear to be random dots on our page with no real pattern, so we would say that there is no relation there. Now we say that two variables that are linearly related are positively associated when above average values of one variable are associated with above average values of the other variable. And consequently, below average values of one are associated with below average values of the other. Now, another way we could say that is to say that whenever one of the values of one of the variables increases, the value of the other variable is also going to increase. And if we take a look back over here, this would be an example of a nice positive relationship, or two variables that are positively associated. Now, negatively associated is pretty much the exact same thing, except just opposite. So if one of the values, or if the value of one of the variables increases, the value of the other variable is going to decrease. Or we could say that above average values of one variable are associated with below average values of the other. That would be something where we have a negative association. Now, the linear correlation coefficient, or it is also referred to as the Pearson product moment correlation coefficient, is just a measure of the strength and the direction of the linear relation that exists between two quantitative variables. Now, the Greek letter rho actually represents the population correlation coefficient, and little r, which we see more often, represents the sample correlation coefficient. The formulas can be found in your textbook, but we're going to rely on technology, in particular StatCrunch, in order to compute this measure. So there are some properties we want to be familiar with for the linear correlation coefficient before we actually use technology to compute it. The first is that the linear correlation coefficient is always going to be between -1 and 1 inclusive, meaning that we can have a linear correlation coefficient of -1, we can have a linear correlation coefficient of +1, or it can be somewhere in between those two values. Now, if we have a linear correlation coefficient of +1, then that means that we have a perfect positive linear relation that exists between the two variables. Now, this would never actually be seen in real data, okay? At least not something where we're just observing something that's already happening, okay? But that would be just kind of your benchmark. If you have something that's very close to +1, then you have something that is a positive linear relation. If you have a linear correlation coefficient that is -1, that would mean that you have a perfect negative linear relation. Now, the closer that the value is to +1, the stronger the evidence is that there's some kind of positive association, and the closer the value is to -1, the stronger the evidence that you have some kind of negative association. Now, if you think about it, if r is close to 0, that would kind of mean that there's little or no evidence of any linear relation. So it doesn't mean that there's no relation at all, it just means that there is no linear relation. So if you recall a couple of slides back, we looked at something that looked like a parabola. That clearly had a relationship, just not a linear one. So that would be an instance where we might get an r that's close to 0. That just implies that there's no relation, but not... or does not imply that there's no relation, just that there's no linear relation. Now, the linear correlation coefficient is a unitless measure of association, so the unit of measure for x and y plays absolutely no role in the interpretation. And the correlation coefficient is not resistant. So we talked about resistant last week when we talked about the mean and the median, but an observation that does not follow the overall pattern in the data could affect our value of our linear correlation coefficient fairly significantly. So if we take a look at these graphs here, you can kind of get used to seeing different scatter plots and what the associated value of r might be. So if we take a look down here, we have a perfect positive linear relation. So all of these points are exactly in a straight line. Okay, so this is going to be something where your little r, your sample linear correlation coefficient, is exactly 1. Now if we scoot over here, you can see that we still have a very positive linear relation between our explanatory and our predictor variables. This one might be an example of something where we have an r that's very close to 0.9. So very close to 1, but not exactly 1. And this is still considered strong. Now if we take a look at this, we still definitely have some kind of positive linear relation, but this one we might refer to as moderate. This would have a value of r that's closer to 0.4. Okay, so there's still some kind of pattern here, which makes it relatively close to 1, but also fairly close to 0, just because they are quite far apart, okay? We have quite a bit of randomness happening here. Now, if you look at D, we have a perfect negative linear relation, so this is r equals -1. We have a strong negative linear relation down here. Again, these are very close to a straight line, but this would maybe be an r that's very close to -0.9. So again, very close to -1, but not equal to -1. And this is an example of a moderate negative linear relation. It looks very similar to this one over here, but there's a negative pattern, sort of a downward slope. Now, if we take a look at G, this one is going to have an r that's very close to 0. There's no linear relation, and there's really kind of no pattern that we can discern from these. But if we take a look over here, this one also has an r that's going to be close to 0, and we would say that there is no linear relation, but there's definitely some kind of relationship between our explanatory and our response variables. So if we want to determine the linear correlation coefficient of our drilling data, we're going to use StatCrunch, okay? So I'm just going to navigate over there real quickly. So I am going to close out of my scatter plot. And where we're going to be going in StatCrunch for the remainder of all of the things we're doing today is just stat, regression, and then simple linear. And then at this point, all we do is we select our x variable and we select our y variable. And we don't need to make any other changes here, and we can just go ahead and click compute. And at this point, there's a lot of information here. We'll worry about reading more of this in a minute, but all we actually care about is this correlation coefficient right here, which in our case is 0.77282. Here's some more digits as well for it, but that is our nice little linear correlation coefficient. Now, you might say this 0.77, is that close to 1? What is it close to? Is it strong enough? Okay, so we do have a way of actually testing to see if there is a linear relation. So the first step is to determine the absolute value of the correlation coefficient. And then we have a critical value table. Now this is in table 2, so if you were in class, I did pass out the tables, okay, and you are able to look at table 2 on those worksheets that I passed out. If you were not there, or if you're listening from an online class, you're able to just go either to your ebook, or if you have a physical textbook and access your tables, you're going to pull out table 2 from the appendix, and you're going to look for the given sample size. And then if the absolute value of your correlation coefficient is greater than the critical value, then we say that there is a linear relation that exists between the two variables. Otherwise, there's none. So if we take a look at the example that we had, we want to determine if a linear relation exists between the time to drill 5 feet and the depth at which the drilling begins. So we know that the correlation that we found between the two variables was somewhere around 0.773. This is a rounded value. That was found on the previous slide. And if we take a look, we have 12 observations in our data. Okay, so we're just going to look on our table 2. This is a little screenshot of table 2. And if you look at sample size 12, you'll see that the critical value is 0.576. Now, since our linear correlation coefficient is greater than 0.576, we can say that there is a linear relation between the two. And since our linear relation is, or our linear correlation coefficient is positive, we can say that there is a positive linear relation between the time to drill 5 feet and the depth at which the drilling begins. Now, one kind of note here, according to data obtained from the Statistical Abstract of the United States, the correlation between the percentage of the female population with a bachelor's degree and the percentage of births to unmarried mothers since 1990 is 0.940. Now, you'll notice that that's a very large value for a linear correlation coefficient. So what we want to talk about is, does this mean that a higher percentage of females with bachelor's degree causes a higher percentage of births to unmarried mothers? And certainly that's not the case. The correlation exists only because both percentages have been increasing since the 90s. So a lot of times when we're looking at time series data, this is going to be the case. The relation that causes the high correlation is the actual year, okay? So since we have data that's collected over time, we're going to have high correlations with a lot of things because we know that a lot of things are either increasing or decreasing over a specified time. So it's possible to have really high correlations and still have something where we don't have one variable causing another. So when data is observational, we can never claim a causal relationship between two variables. You can only claim causality when the data is collected through a designed experiment. And this is something we talked about all the way back in chapter 1. Now, another way that two variables can be related, even though there's not a causal relationship, is through a lurking variable. And a lurking variable is just a variable that is related to both the explanatory and the response variable in some way. So, for example, ice cream sales and crime rates both, when we look at them together, have a really high correlation with one another. So it doesn't mean that local governments should shut down ice cream shops because ice cream sales are not causing crime rates to increase. But in this case, if you're thinking about seasons, the lurking variable is going to be temperature. So as air temperature rises, ice cream sales and crime rates both rise, okay? And as it gets cooler outside, we're not going to have as many ice cream sales and crime rates are going to go down because people are going to be inside. So that's just kind of a seasonal effect that we see. So it obviously doesn't mean that ice cream sales and crime rates are causing one another in any way, okay? But they do have a very high correlation when we actually look at the correlation coefficient. And you just need to be aware of the fact that we have these lurking variables and we have these issues with time series data that cause us to get really high correlations, even when one thing doesn't necessarily cause the other. Okay, so now we're going to move on to the actual regression. Okay, this is section 4.2. We're going to talk about least squares regression. So one kind of definition here first, before we talk about the least squares regression line, is what we call the residual. So the difference between the observed value of y and the predicted value of y is called your error or your residual. So the whole point of the least squares regression line is to minimize the sum of the squared errors, or you could call it the sum of the squared residuals. So the line that minimizes this sum is our least squares regression line. Now, if you see this notation down here, we just say that we're minimizing. This right here is a summation symbol, okay? And so what this really means in just plain old English is just that we're minimizing the sum of the squared residuals. Now, the line is going to just minimize the sum of the squared vertical distance between an observed value of y and a predicted value of y, which is going to be predicted by our line. Now we call our predicted values of y our y hat. So let's use our drilling data to actually find a least squares regression line and then do some predictions. So in order to find the least squares regression line, it's very tedious by hand. I do have an example in the lecture notes that walks through a way that we can find the least squares regression line if we're already given some summaries of our data, and that's not too difficult. But you're going to want to rely on either Excel or StatCrunch to probably actually create the least squares regression line for you most of the time. So in StatCrunch, we're going to go to regression, simple linear regression, and we're going to get these values out. So we actually already did this, but let me close out of this to just show you again. But if you go into Stat, Regression, Simple Linear, and I'm going to select X as my depth and Y as my time to drill and hit compute. This is the same way that we got our linear correlation coefficient, the 0.773 value, that was this right here. And we were also given all of this other information. And you'll notice in my screenshot, I just took a screenshot of a little part of it, okay? Just this piece right here where we have the intercept of 5.527 and the slope of 0.01155, okay? Now, if you recall, in general, the slope of an equation of a line is going to be y equals mx plus b, where m is the slope and b is the y-intercept. This is your slope-intercept form, so hopefully you're all comfortable with this. This should be definitely a review for you, okay? Now it's very easy to put these pieces together to actually create the equation of the line. So the equation of your line is always going to start with y hat because that's a prediction. So the little hat above it kind of indicates that we're saying that it's not an actual y value, it's a predicted y value. So y hat equals our slope, which was given up here. I rounded to 4 decimal places, so it's 0.0116 times x plus 5.5273. Again, rounded my y-intercept as well. And if you recall, the x is going to stand for the depth at which drilling began, and our y hat is going to be our predicted amount of time that it will take to drill an additional 5 feet, given our x value. So if we want to actually use our nice little regression equation that we created, we can use it to predict different values. So let's say, for example, that we want to predict the drilling time if drilling starts at 130 feet. So all we need to do with our 130 feet is just plug it in for x, because we know that x stands for the depth at which the drilling begins. So if we take our nice little equation here and we plug 130 in, multiply that by our slope, and add on our y-intercept, we're going to get 7.035. Now this gives you, this says seconds down here, but this should actually be minutes. I believe all the drilling data is in minutes. So that means that at 130 feet, it's predicted that it would take 7.035 minutes to drill an additional 5 feet down. Now, the actual observed drilling time from our actual raw data that was collected was 6.93 seconds. Now, what we predicted was 7.035. So our predictions are normally not going to be right on the nose, but typically they're going to be pretty good. And so what we can say in this case is that the drilling time of 6.93 seconds is actually a little below average. We would expect it to take a little longer. And I apologize, when I said seconds there, I should have said minutes, and these should all say minutes right here. So in terms of interpreting the slope, this is a really important concept, okay? So it's important that when you create a regression equation, you actually understand what the values mean and how they can be used in the context of the question. So we know that the slope of the regression line is 0.0116. So what this really means is that for every additional foot of depth that we start drilling, the time in order that it takes to drill 5 additional feet increases by 0.0116 minutes on average. Now, the interpretation of slope in general should normally go something like this. You should normally say for every 1 unit increase in whatever your x variable is, which in our case is depth, okay, or depth in feet, you say that your y variable, which in our case is time, in minutes, and then you can say that it either increases or decreases. Now you pick this word based on the value of your slope. So if you have a positive slope, it's going to increase. If you have a negative slope, it's going to decrease. And then you just put the value here, and you always want to say on average. So if we take a look at how this fits in with what we're saying up here, we just say that for every 1 unit increase in depth in feet, our time to drill 5 additional feet increases by 0.0116 minutes on average. Okay, so you can just see we're using the exact same setup that we had down here. We're just plugging in sort of the relevant information. So this might take a little bit of getting used to, but really that's what the slope is kind of describing. It's saying for every 1 unit increase in your x, or your explanatory variable, it's telling you how much your y, or your response variable, changes. It either increases or decreases by the slope value. Now we can also interpret the y-intercept, and in our case the y-intercept of our line was 5.5273. So there are a couple of questions that we have to answer first. And the first is to kind of ask yourself, is 0 is a reasonable value for the explanatory variable? And then if any observations that are near x equals 0 actually exist in your data set. So in our case, 0 is a reasonable value for x because we could start the drilling at the surface of the Earth, which would be a depth of 0. Now, the smallest observation that we had in our data set is 35 feet. That could kind of go either way, but it's reasonably close to 0, so I think it's okay to provide an interpretation of the y-intercept. So really what we would say for the interpretation is that the time to drill 5 feet when we begin when we begin drilling at the surface of the Earth, or when we begin drilling at depth of 0, is going to be the value of our y-intercept, which was just 5.5273 minutes. Now, there's kind of a caution sign here. If the least squares regression line is used to make predictions based on values of the explanatory variable that are much larger or much smaller than the observed values, then we would say that the researcher is kind of working outside of the scope of the model. So we never want to use a least squares regression line to make predictions outside of the scope of the model, because we can't be completely sure that a linear relation continues to exist. So we can't assume that just because it has been increasing up until this point that it continues to increase in the same sort of way. So we want to make sure that when we're using our regression equation to predict, that we're predicting within the scope of our model. All right, now the last section is section 4.3, which talks about the coefficient of determination. Now, the coefficient of determination, it's also called r squared, and it measures the proportion of the total variation in the response variable that's actually explained by your least squares regression line. So the coefficient of determination is a number that's going to be between 0 and 1 inclusive, okay? So that is to say that 0 is less than or equal to r squared, which is less than or equal to 1. Now, if you have an r squared value of 0, that means that their line really provides no explanatory value. It's not really useful. If you have an r squared value of 1, it means that your line explains all of the variation in the response variable. So it's a perfect model. Not very likely that you're going to get either a line that explains none or that explains everything. Somewhere in the middle is kind of more typical. But those are sort of your benchmarks to work from. So a couple of sort of definition things here. This just kind of helps you see how our r squared value is calculated, okay? It's important to understand these different types of deviations that we have. So the total deviation is going to be equal to the difference between our observed value, which is going to be our y value, and the mean value of the response variable. Now, our total deviation is made up of two pieces. We have explained deviation and unexplained deviation. So for explained deviation, what that is it's just the difference between our predicted variable, which is our y hat. So hopefully you remember the little hat on top tells us that that's a predicted variable, or a predicted value. So it's the difference between our predicted value, our y hat, and the mean value of the response variable, which is going to be y bar, okay? And that's going to be the deviation that can actually be explained. And then we also have unexplained deviation, which is found by taking your observed value and subtracting the predicted value. Now, the better your equation is at making all of your data points very close to the actual observed values, the smaller this unexplained deviation will actually be, which will in turn make your r squared value higher, okay? So the higher the r squared value, the better your equation. So if you take a look at this, if you're kind of a visual person, this might help you a little bit. Let's say that this is our this is our explanatory variable down here, our x, and this is our response variable down here. And this black line right here represents y bar, okay? That's our average for our response variable. And then we have this line right here, which represents our x bar, which is the average for our explanatory variable. And then we have this blue line right here, which was created as our regression equation. And if you look here, this dot, which is directly on our regression equation, is just one piece that was picked directly from our regression equation. And its coordinate is given by x, y hat, because it's a predicted value. And then this dot up here represents an actual data item, which is just x, y. So this is something that was actually observed. So if you look at the total deviation, that's going to be the distance from your actual observed data and the average. Okay, so it's going to be this entire thing right here. And if you look, it's broken into two pieces, just like we explained on the previous slide. We have unexplained deviation, which is from y all the way to y hat, okay? And this is the value that we want to minimize, okay? It's our residual. It just gives us basically our error, how far off our line was from our actual data point. And then we also have our explained deviation, which is the distance from our predicted value to our mean. So the total deviation is just found by adding those two things together. Now, in order to determine an R-squared value for a linear regression model, all you really have to do is just square the value of the linear correlation coefficient. Now, squaring this linear correlation coefficient to obtain the coefficient of determination only works for the least squares linear regression model, which is all we're going to be dealing with in this class, but it's important to note that this method does not actually work in general. It's just going to work for our nice little least squares linear regression model. So let's say that we want to find and interpret the coefficient of determination for the drilling data. It's pretty easy because we already have our linear correlation coefficient of R, which was 0.773. So all we have to do is take that value and square it. And then we've kept a couple decimal places here, and we've changed our value into a percentage because when we're interpreting our R-squared value, you want to make sure that you're interpreting it as a percent. So our R-squared value is 59.75%. So what we would actually say is that 59.75% of the variability that exists in drilling time is explained by our least squares regression line. So what that means is that almost 60% of the variability that exists in that drilling time is actually explained just by using the information that we obtained about where we are starting our drilling, or the depth of the drilling. So if you take a look at these data sets right here, you can kind of see a couple of examples where we have different R-squared values. So if you look at data set A here, we have a regression equation. And this one, if you look at the black dots and the blue line, you'll notice that the black dots all lie almost directly on the blue line or very, very close to the blue line. So this is an example of something where we have an R-squared value that's very, very close to 1, which would correspond with 100%. So this one, they estimated it to be 99.99%, okay? So our R-squared value is 0.9999. So what that actually means is that 99.99% of the variability in our Y variable is explained by our least squares regression line. Now if you take a look at data set B, this one does a pretty good job of fitting to our data. We have a couple of data items or data points that are very, very close, and we have some that are a little further away. This one still has a very strong R-squared value of 0.947, which corresponds to 94.7%. So what that actually means is that for data set B, 94.7% of the variability in Y is explained by the least squares regression line. And then if we take a look at data set C over here, this almost looks random. It does not look like we have a very strong relation at all, particularly not a linear relation. It doesn't really look like any type of relation to me. And if you look at this least squares regression line, there are a couple data points that are really close, but there are many that are very far away, okay? So this would be an example where we have an R-squared value that's pretty close to 0. In our case, it looks like an R-squared value of 0.094, which would correspond to 9.4%. So we would say that 9.4% of the variability in Y is explained by your least squares regression line. Now, one other quick thing that I want to point out is that StatCrunch also gives you this R-squared value out. So it gives you the linear correlation coefficient, and then right below, it also gives you this R-squared value. So that is it for Chapter 4. If you have any questions about anything, please feel free to contact me.